This is the beginning of our second theme, entitled The Universe's Geometry and Expansion History. This theme occupies, at least to my mind, a rather unusual niche in cosmology. It's almost completely unconcerned with the detailed nature of the universe's contents. For the next 3 lectures, you'll barely hear mention of stars or galaxies, and instead, we'll view the universe as uniformly filled with simple, featureless stuff, whose only property is that it generates and responds to gravity. This theme is also our oldest. Most of the ideas we'll be looking at were developed in the 1920s and 30s, so everything has a rather classical feel to it. The theme is also our most theoretical. We'll be thinking about how to apply simple yet deep principles of physics to certain imaginary universes, to see how they might behave. As long as the physics is applicable, then our imaginary universes should match the real universe. I think it's also true that this theme provides the bedrock of cosmology. All the other themes rest, explicitly or implicitly, on this foundation. And without it, in a sense, we'd be nowhere. Now, the reason for its importance isn't hard to grasp. We'll be considering the construction and development of the stage on which the entire cosmological play unfolds. In our case, there are 2 aspects to this framework. The first is the nature of the space that holds the universe's contents. That's for this lecture. And the second is how that space changes over time, and that's the next 2 lectures. So let me start by posing 2 subtly different questions. What is the universe's shape, and what is the universe's geometry? We think of shape as the boundary of a region, a sphere or a disk, or maybe a pencil shape. We really can't apply this concept to the universe since it has no boundary. Remember from lecture 3, the universe obeys the cosmological principle. It's isotropic and homogeneous, so it's the same everywhere. So there is no center, and there is no edge. It has no shape. Now, geometry is an altogether subtler concept, and it's rather tricky to intuit. So let's start with a kind of geometry we're all familiar with, because we all learned it at high school. It's called Euclidean geometry, after the Greek mathematician Euclid of Alexandria. Here are some of the most well-known Euclidean results. The interior angles of a triangle add up to 180 degrees. The circumference of a circle is 2 pi, that's a bit over 6, times the radius. The surface area of a sphere with radius r is 4 pi r squared, and its volume is 4/3 pi r cubed. Now, the reason we spent our time as children learning these formulae is that they're correct for the space in which we live. Well, almost. The amazing truth is that if you were to make extremely accurate measurements, you'd find these formulae didn't quite work. They'd be very slightly off. The reason is that within a gravitational field, like the Earth's, the nature of space and time is changed slightly, and this in turn modifies the rules of geometry. Now, this whole subject was explored in 1915 by Einstein in his famous theory of general relativity, which is all about space, time, mass, and gravity. This theory is extremely important in cosmology because gravity doesn't just affect how the universe expands, it also affects the nature of space and time. So remarkably, general relativity actually allows us to analyze the entire space and time that holds the unfolding universe. Now, one of the things general relativity does is to combine space and time into a single entity called space-time, which has a form that is, in a sense, warped by the mass that's spread throughout it. Now, in most situations, the space-time is warped in a complex way, like near the sun or near black holes. But in cosmology, the mass is spread about uniformly, and this enormously simplifies the warping. Not only are the space and time parts cleanly separated, but the space part is warped, curved in a particularly simple way. Now, getting your mind around curved spaces is really quite tricky, but let's have a go. I'm going to describe what it would be like living in a curved space, whose curvature radius is about 4,000 miles, meaning we begin to notice non-Euclidean effects across distances of a few thousand miles. So nearby, everything seems pretty normal. Constructing triangles and circles a few miles across, all our high school Euclidean rules work just fine. But now, let's go bigger. Imagine I have a lightweight, perfectly straight pencil with an adjustable length. It's a bit like a laser pointer, so I can sweep it around and draw huge circles. I can then walk over to the circle and pace all the way around it to measure accurately the circumference. So let's set this pencil length to 2,000 miles. It's a very big circle. Now, in a Euclidean space, we'd expect all the way round to measure a circumference of 2 pi times 2,000 miles. But in our curved space, after carefully measuring the circumference, we come up 500 miles short. Very puzzling. Now, you can repeat this in different planes and also from different locations. Same thing, always 500 miles short of 2 pi times 2,000 miles. So we're not at the center of some weird distortion. This is a global effect. We are in a non-Euclidean geometry. Now, if we repeat this for circles of different radius, this is what we find. Radius is along the bottom, circumference is up the side. Now, the circumference should follow this straight line. C equals 2 pi r. But we're finding the circumference is falling short by an increasing amount for larger radii. Most bizarrely, the circumference goes through a maximum and then drops and goes to 0. Imagine this. I have a 12,500 mile pencil. I move it all the way around the sky, and its distant point remains stationary. Now, at this point, you should be feeling profoundly bewildered, and that's perfectly okay, because our brains simply cannot grasp this intuitively. It's just not possible. However, an analogy does help shed some light on what's happening. Let's replace our curved, three-dimensional space with a curved, two-dimensional surface, a sphere. And to match the size of the curved space, our sphere needs to be really big. With radius 4,000 miles, it's Earth-sized. Now, in this two-dimensional curved world, my laser pointer pencil goes out around the sphere. Its radius, r, is the arc, and the circle it draws is this line. When the radius is small, the circumference is very nearly 2 pi r. But as the radius increases, the circumference follows exactly the graph I showed you before. The maximum circumference is around the equator, and from then on, it gets smaller. When the pencil is 12,500 miles long, its tip is at the antipode, and as the pencil swings around, the tip never moves. It's because of this close similarity between the behavior of a non-Euclidean three-dimensional space and a curved two-dimensional surface that we say the three-dimensional space is curved. Notice that with the three-dimensional space, nothing actually curves into anywhere. Our laser beam is always straight, but the normal Euclidean relationships get modified in exactly the same way that they do if we draw shapes on a sphere rather than on a plane. In fact, here are the new rules for our non-Euclidean space. A circle's circumference is less than 2 pi r. A sphere's surface area is less than 4 pi r squared, and its volume is less than 4/3 pi r cubed. And the sum of a triangle's interior angles is more than 180 degrees. Finally, and perhaps most intriguingly, the volume of our curved three-dimensional space is finite. You can see why. Walk off in any direction, and after 12,500 miles, you pass the antipode, and after a further 12,500 miles, you are back where you started. Now repeat that for all directions, and you would have been everywhere. There's nowhere that you hadn't passed through. Notice you encounter no edges and no boundaries, and yet the space has finite volume. This whole situation is actually mirrored in our sphere analogy very nicely. Its surface has a finite area, and there are no boundaries on it. Two final pieces of terminology here. Because the space mirrors the sphere, we say its curvature is positive, and because its volume is finite, we say its geometry is closed. Now, I say this to contrast with a second kind of non-Euclidean space that has negative curvature and is open. In this kind of space, all the geometrical relations are opposite. A circle's circumference is more than 2 pi r. A sphere's area is more than 4 pi r squared, and its volume is more than 4/3 pi r cubed, and the sum of the angles in a triangle is less than 180 degrees. Here's the graph that shows how the circle's circumference gets much bigger than 2 pi r. Now, since everything gets bigger at larger distances, the total volume is infinite, and that's why the geometry is said to be open. Unfortunately, there's no simple two-dimensional surface analogue for the open geometry, although the centre of a saddle does match the space at just one point. Okay, so to summarise, there are three geometries whose spaces are homogeneous and isotropic. Zero curvature, or flat, which is Euclidean. Positive curvature, which is closed. And negative curvature, which is open. Now, at this point in the lecture, our universe could have any one of these three geometries. Okay, let's now look at the time part of the cosmic space-time. The first people to realise how space and time might be packaged together for the universe were the American and British mathematicians Howard Robertson and Arthur Walker in 1935. So this particular space-time is called the Robertson-Walker space-time. And here's a non-mathematical way of describing it. So time enters in two ways. The first is very simple. Time just flows along nice and uniformly for everyone. This is called cosmic time. And its value is 0 at the Big Bang, and from then on, the seconds tick away everywhere at a uniform rate. The second way in which time enters is to make the space part expand or contract uniformly. This enters via our old friend from earlier lectures, the size or scale factor S of t. It scales the entire space. Now, back in our two-dimensional analogue, this is easy to visualize. The sphere expands. Now, an obvious consequence of this is that all points get further from each other. In fact, if you look carefully at how they separate, you'll find that the points that are further apart also move apart more quickly. And this is the Hubble law. So one of the natural consequences of the Robertson-Walker spacetime is that the universe should be expanding or contracting uniformly, and objects embedded in the expanding space should obey the Hubble law. Now, in the rest of this lecture, I want to talk about attempts to find out what the true geometry of our universe is, whether it's curved or not, and if so, what its curvature radius is. And in the next 2 lectures, I'll be talking about the universe's expansion history, S of t. So let's begin by clarifying what determines the curvature of space. It's really just 2 things: the universe's density and its expansion rate. Universes with higher density and/or slower expansion have more closed geometries. This is kind of how you might expect things to be. A higher density is going to curve space more and so make it closed. As you might have guessed, lying right between closed and open geometries is a flat geometry, and it involves just the right combination of density and expansion speed. Here is that combination. If the ratio of the expansion speed squared to the density is 8 pi g over 3, where g is Newton's gravitational constant, then the curvature is 0 and the geometry is Euclidean. Now, in math form, we have h0 squared over rho is equal to, 8 pi g over 3, where h0 is Hubble's expansion constant, and as usual, we use the Greek letter rho for density. Now, since we know the Hubble's constant pretty well, cosmologists usually rearrange this equation and talk about a critical density, rho critical, equals 3h0 squared over 8 pi g. If you put in the measured value of h0, that's, remember, 22 kilometers per second per million light years, you get the extremely tiny density of 9.7 times 10 to the minus 27 kilograms per cubic meter. That's equivalent to about 5.8 hydrogen atoms per cubic meter. Now, the critical density is an exceedingly important concept in cosmology. If the average density of the universe is more than the critical density, the geometry is closed. If it's less than the critical density, the geometry is open. Now, before I tell you which geometry our universe actually is, there are a few things I want to say about cosmic densities. So first, you won't be surprised to hear that the density, rho, in this formula refers to all forms of mass and energy. They all add to curvature because they're all creating gravity. So from lecture 4, here are the 5 cosmic components: dark matter, atomic matter, photons, neutrinos, and dark energy. For the energy of the photons, neutrinos, and dark energy, we just use E equals mc squared to convert them to their equivalent mass densities. And then we simply add all of these densities to get the total density, rho total. Now, all these densities are exceedingly tiny, so cosmologists usually quote them as multiples, or fractions, of the critical density. And these rescaled densities are given the Greek symbol omega. So our sum of densities can also be written as the sum of these omegas. So we now have the following simple rule. If omega total is greater than 1, the universe's geometry is closed. If omega total is less than 1, the geometry is open. And if omega total equals 1, the geometry is flat or Euclidean. So let's now return to our primary goal, establishing the universe's true geometry. We have 2 rather different approaches. One is to measure the component densities, add them up, and see what omega total is. And the other is to try to use one of those geometrical methods to measure the deviation from the Euclidean rules. Now, over much of the 20th century, huge effort went into both of these approaches, with success only arriving at the very end of the century. So let's start by adding up the densities. The photon and neutrino components are tiny, so for our purposes, we can just ignore them. Now, in lecture 25, I'll describe a pretty robust way to measure the total atomic matter density using nuclear fusion reactions in the early universe. And that gives an omega of only 0.04. So that's well below what's needed to close the universe. What about dark matter? Remember in lecture 9, I described various ways to measure the amount of dark matter in the universe, coming up with an omega of about 0.23. So when we add that to the atomic matter, we're up to only 0.27. Still not enough to close the universe. Now, for many years, that was actually the basic result. It seemed we live in an open universe, though, in fact, many cosmologists, particularly theorists, suspected there was more to the story, mainly because inflation should give the universe Euclidean geometry with an omega total of 1.0. And then, sure enough, in 1998, by carefully measuring cosmic expansion, dark energy was discovered as a fifth cosmic component with an omega near 0.7. So that brought the total omega up to about 1. Apparently then, we live in a universe with Euclidean geometry. But of course, for a result of this importance, it's vital to check independently by measuring the cosmic geometry directly, by looking for deviations from the Euclidean rules. Now, despite decades of failed attempts to measure the universe's geometry, at the very end of the 20th century, a reliable method was finally found. And it involves using a cosmic ruler of known length to test the circle circumference relation. Is it greater or less than 2 pi r? Now, actually, we don't need to use the full circle, just a small slice will do. The arc length is just the circumference multiplied by this fraction, theta, over 360. So if you know the arc length, L, and the radius, r, and the angle, theta, then you can measure the curvature of the space. Of course, the bigger the radius, the better. And you can't do better than from here to the microwave background. That's literally as far as you can see. So what we need is a feature on the microwave background whose physical length we know. Now, in lectures 15 and 16, we'll learn there are sound waves visible on the microwave background. And amongst these sound waves, there is a particularly strong fundamental tone with a specific wavelength. Now, the physics of the young universe is sufficiently simple that we can calculate that wavelength and be confident that we're correct. It's about 600,000 light years long. That's our arc length, L. Now, it turns out we do also know the distance to the microwave background quite accurately, actually partly because we know when it was formed. So we know r, the radius. Now, with such a huge radius, the curvature distortion is actually quite large. In fact, on our earlier plot of deviations from Euclidean, you can see that for omegas larger than 1.2, the microwave background is actually over the peak, beyond the sort of equator. Now, alternatively, for an open universe with an omega of just 0.8, there is a 50% difference from Euclidean, the other way. So this should be a pretty sensitive test. So here's the graph that shows the expected angular size for our specific acoustic wavelength seen on the microwave sky. It goes from about 0.3 to 2.5 degrees for an omega total, going from about 0.5 to 1.5. Actually, these sketches help show what's going on using the two-dimensional surface analog. The patches on the microwave sky look smaller in an open geometry and larger in a closed geometry because the universe's curvature acts like a giant lens. With zero curvature in the middle, the rays don't bend and there is no magnification or demagnification. While a closed universe acts like a convex lens, it bends the rays but makes the patches look bigger. An open universe is like a concave lens. It bends the rays and makes the patches look smaller. So what do the data show? What are the real patch or wavelength sizes? Now here's a diagram we'll look at in much more detail in lecture 15. It shows the strength of the sound waves up the y-axis against their size on the microwave background along the x-axis, with big waves on the left. For our present purposes, just notice that there is a strong peak for waves with size 0.82 degrees, with about 1% uncertainty. This is the angle theta for our 600,000 light-year waves. They're really remarkably well measured. So, what value does that imply for the curvature? Back to our graph. Here's the angular size, and it corresponds to an omega total of 1.01 plus or minus 0.015. The geometry of the universe, as best we can measure, is Euclidean. Giant triangles do add up to 180 degrees. Giant spheres do have surface area 4 pi r squared and volumes 4/3 pi r cubed. All the geometry you learned at high school applies, not only to surveying your property, but also to surveying billion light-year galaxy maps. This is a fabulous scientific result and should go down in history as a truly great achievement. I mean, after all, we still teach how Eratosthenes first measured the radius of the Earth back in 200 BC. Surely, measuring the geometry of the universe is at least as memorable. Let me end this lecture making 2 points about this relatively recent result. The first is to notice that it raises the question of why the universe's geometry is flat. Of all the possible densities the universe might have had, somehow it chose exactly the right one to make the curvature zero. That's a very special condition, balanced on a knife edge between closed and open. This must be telling us something deep about how the universe is constructed. In fact, specifically, how the expansion was launched. As we'll see in lecture 31, the process of inflation naturally flattens space and generates exactly this kind of Euclidean universe. Now, my second point is that this result implies that the universe is much bigger than our currently visible horizon. It's like doing a land survey on Earth. If it spans a dozen miles, you'll deduce the surface of the Earth is flat to high accuracy, but only because the Earth is so big. On this sphere, this circle has about 1% deviation from Euclidean. So if that is our visible universe, then the whole universe is at least this much bigger. Its curvature radius is at least 150 billion light years, and it contains at least 10 to the 15 galaxies. Now, the reason I say at least is that in the future, our accuracy will increase. In fact, we expect the observations to show ever more precisely a flat geometry, mainly because inflation's ability to flatten space is so powerful, suggesting that this ball could be miles across or even the size of the Earth. And this would still be our 14 billion light-year visible universe. But I'm going to leave these possible extreme dimensions for later lectures and briefly summarize this lecture. Our topic was to understand the character of the space and time within which the entire universe unfolds. The all-important framework for thinking about this is Einstein's general theory of relativity. At its core, general relativity sees mass and energy as warping a four-dimensional space-time. And although the warp is normally quite complex, when the mass is distributed uniformly, as it is in the universe, the warp is particularly simple. Everyone experiences the same uniform cosmic time, and space uniformly expands or contracts with a Hubble law. The space need not, however, obey the Euclidean rules we've learned at high school, but can be curved in ways that are difficult or impossible to visualize, though two-dimensional surfaces can help us slightly. Now, for a given cosmic expansion, the crucial property that sets the cosmic curvature is the average cosmic density. For our current Hubble constant, we find a critical density of about 5.8 hydrogen atoms per cubic meter that generates a space with zero curvature, a Euclidean space. Above the critical density, we have a positively curved closed space, while below the critical density, we have a negatively curved open space. When we try to measure the total cosmic density, we find dark and atomic matter add up to about 27% of the critical density, but adding in dark energy, measured from the expansion history, brings this up to about 100%, suggesting the geometry is flat. Actually, measuring cosmic curvature directly has proved extremely difficult, but was finally achieved using sound waves of known wavelength on the microwave background to check the arc-angle relation across the entire visible universe. The result is as beautiful as it was a technical triumph. To within 1% accuracy, the curvature is zero. The geometry is Euclidean. This immediately makes the theory of inflation much more credible, since zero curvature is a direct prediction of inflation. It also means we live in a truly huge universe. Even the most distant galaxies are close by comparison to the universe's true extent.